Have you ever looked at a tiny little computer chip and wondered how in the world it can control something big and powerful in the real world? Well, today, that's exactly what we're going to do. We're going to bridge that gap between the low-power digital brain of a microcontroller and the high-power physical muscle of a device. It's going to be fun. Let's dive in. So here's the puzzle we're trying to solve. Over here, we've got our ESP32 microcontroller. It's an amazing little computer, but its brain runs on just 3.3 volts. And on the other side, we have this big, beefy 12-volt solenoid lock. So the question is, how do we get this little guy to boss around the big guy?
Okay, let's get specific. Our mission, should we choose to accept it, is to use this ESP32 to operate this 12-volt lock. The whole idea is to send a simple command from our computer and see this physical lock actually spring to life. Now, you can't just hook the lock straight up to the ESP32. I mean, you could try, but you'd have a very bad day. The GPIO pins on the board just can't handle the 12 volts that lock needs. It would instantly fry the board. So, what we need is an intermediary. We need a helper that can do the heavy lifting for us. And that helper is this little guy right here. Meet the TIP120 Darlington transistor. This small, three-legged component is the absolute key to making this whole project work. You can think of it as our electronic muscle.
So what exactly is a Darlington transistor? Well, the best way to think about it is like an electronic lever, or maybe a supersensitive switch. We can use a tiny, weak signal from our ESP32 to poke it, and in response, it opens up a massive floodgate for a much bigger, high-power current to rush through. It's all about a small push controlling a big force.
The TIP120 has 3 legs or pins, and each one has a really simple job. First, you've got the base. That's our trigger. It listens for the small signal from the ESP32. Then there's the collector, which you can think of as the input for the big power. That's what we'll connect our lock to. And finally, the emitter is the output that connects to ground, completing the circuit whenever that switch is flipped on.
All right, theory's cool and all, but let's actually get our hands dirty and build this thing. But as we start putting it together, there's a sneaky little danger we have to watch out for. If we don't, we could easily destroy our components. Let me ask you this. Our solenoid lock is basically an electromagnet, right? It's just a coil of wire. So, what do you think happens when that powerful magnetic field inside the coil suddenly collapses the very instant we cut the power?
Well, what happens is something called back EMF. The moment that field collapses, the coil generates this huge, nasty reverse voltage spike. And trust me, that spike is more than powerful enough to kill our transistor and maybe even take the ESP32 with it.
This back electromotive force, or back EMF for short, is just a natural thing that happens with things like motors and solenoids. It's this powerful kickback of energy that has nowhere to go, except right back into our sensitive circuit, and we absolutely have to protect our gear from it.
Luckily, the solution is really simple and elegant. It's a tiny component called a flyback diode. When we put it in the right spot, it basically acts like a shield. It catches that nasty voltage spike and gives it a safe little loop to run around in until it fizzles out, keeping the rest of our circuit completely safe.
Okay, let's walk through the wiring nice and slow. First up, the transistor's base pin connects through a 1K resistor over to pin 2 on our ESP32. Simple. Next, the lock's positive wire goes straight to the positive terminal of our 12-volt power supply. The lock's negative wire hooks into the transistor's collector pin. Then, the transistor's emitter connects to the 12-volt supply's ground. And last, but definitely not least, our little hero, the flyback diode, goes right across the lock's 2 terminals, making sure that little stripe on the diode is pointing towards the positive side.
Now stop for a second, because this is the single most important tip, and it's a mistake that trips up so many people. You absolutely must connect the ground of the ESP32 to the ground of the 12V power supply. If you don't have a common ground reference, the signal from the ESP32 to the transistor makes no sense at all, and the circuit just plain won't work. So please connect your grounds.
Okay, our hardware is all wired up and it's protected. Now it's time to write the code. This is going to be the brains of the whole operation, telling our circuit exactly what to do and when to do it.
The code gets off to a pretty simple start. First, we just create a variable for our control pin, which is pin 2. Then, inside the setup function, we have to tell the ESP32 that this pin is an output, right? Because we're sending signals out of it. Then we just fire up the serial monitor, which is how we'll talk to the board from our computer.
And here it is. This is the heart of the logic. The program just sits there, constantly checking if any data is coming in from the serial monitor. The moment it gets something, it checks it against our secret password, in this case, 0123. This one line of code is the gatekeeper for the whole system.
So what happens if the password is a match? Well, a little three-step dance kicks off. First, digital write high sends that little 3.3-volt signal to the transistor's base, which tells it to turn on and let the 12 volts flow through the lock. Then, the code just waits for 5 seconds. Finally, digital write low cuts the signal, the transistor turns off, and the lock snaps shut again.
So the hardware is built, the code is uploaded, you know what that means. There's only one thing left to do. It's the moment of truth. Let's see if our little digital key can actually open this big physical lock.
Okay, let's test it out. I've got the serial monitor open. First, let's type in some garbage password and hit enter. And nothing. The lock stays shut. Perfect. But now, let's type in the correct password, 0123, and there it is. That satisfying clunk as the lock pops open for 5 seconds before closing again. It works.
And that right there is a success. We've taken a tiny, low-power digital signal from a computer, used a transistor as our electronic switch, and we've safely controlled a much more powerful high-voltage device. This is such a fundamental concept, and it's the key to so much in robotics and physical computing.
So, what's the big takeaway here? You now have the secret to bridging that power gap. You know, the same exact circuit that controls this lock could just as easily control a motor, a pump, a bunch of high-powered LEDs. The possibilities are absolutely huge. So the only real question left is, what are you going to build with it?